Alright kids, here's discussion 1-1, classifying matter. We're going to look at phases of matter, phase diagrams, and how we classify matter into pure substances and mixtures. Alright, so let's first look at the different states of matter. We know that states of matter means gas, liquid, and solid. So we're going to talk about the shape, volume, and the movement of particles in these different states. Now, let's first focus on the pictures. We can see in these pictures that the gas particles are very far apart from each other. In liquid, they're closer together, but they're not quite as close together as they are in a solid. So let's talk about gases first. Now, when we talk about shape, we're going to talk about whether or not that phase will fit the container that you put it in. So we know that gases have an indefinite shape. If you have a gas in a balloon and you pop that balloon, those gas particles are going to spread out across the room. That means that the shape of a gas can change. Now the volume of a gas is also indefinite. When we talk about volume, we're going to be talking about compressibility, whether you can compress a gas, a liquid, or a solid. Now, because the particles in a gas are very far apart from each other, they can be squeezed closer together, so a gas can be compressed. We often see that in things like helium tanks. You know, the number of balloons that we can blow up with a helium tank is a lot bigger, the volume is a lot bigger than the volume of the gas inside the tank. And finally, the movement of particles. You can also see from the picture that those gas particles are flying around, so they have a lot of energy, so they have high movement. Now let's talk about liquids. Now we all know that a liquid will fit the shape of any container you put it in. So that means it also has an indefinite shape. If you take water and put it in a square container, the water will take the shape of a square. If you put it in a round container, it'll take the shape of a round. Now, as far as the compressibility or the volume of liquids, the volume will be definite. And that's because these particles are close enough together that if you try to squish them any closer together, you just can't do it. And the movement, you can see that they are moving around. Liquids do like to flow, and so we'll say they have medium movement. Now solids. Let's assume you have a chunk of copper. That chunk of copper is always going to have the same shape because these particles are actually locked together. They're connected to each other so tightly that they're basically stuck in place. So solid will have a definite shape. They'll also, for the same reason, have a definite volume. And the particles, they are moving. They're vibrating in place, but they don't really move that much in relation to each other, so we'll say that they have low movement speed. Alright, now a phase diagram. This is a graph that can be used to predict the physical properties of a substance, predict what phase a particular sample of matter will be in at a certain pressure on the y-axis and temperature on the x-axis. So we look here, we have three separate regions in this graph: solid, liquid, and gas. One thing we could do is just plot a point. If we're given a specific temperature and a specific pressure, when we plot the point, if the point falls in the solid region, we would say that at that temperature and pressure, that sample of matter is solid. If we plot a point and it ends up over here in the gas region, we can say that it is gaseous. Now, these lines, because they're the borders between the different phases, also represent phase changes. Right? If we have actually I want to talk about the triple point. So we notice there's a point on this graph called the triple point, and it's the point where all three of these lines intersect on the graph. Now the triple point is a very special place because at the triple point all three phases of matter, solid, liquid, and gas, are existing at the same time. Now let me go back to the phase changes. So if we have our point up here in solid and we increase the temperature, that means we'll be moving along the x-axis. If we heat up that sample enough, it'll cross over the solid line into the liquid region, and we call solid to liquid melting. If we're going back in the other direction, it would be called freezing. Now when we cross the border between liquid and gas, we would call that evaporating. You could also use the term boiling if you wanted to. And if we cross from gas to liquid, it's called condensing. Finally, a phase change that you're probably not familiar with is called sublimation. Sublimation is the transformation directly from solid into gas without passing through the liquid first. So the line representing sublimation would be right here, going from solid to gas without passing through liquid. Alright, so I want you to take a moment and practice. Now this is a phase diagram for carbon dioxide, so answer these two questions. At 200 Kelvin and 5.2 atmospheres, what will the state of matter be? And what phase change is occurring along line C? All right, so pause your video, take a moment and see if you can work that out. All right, so at 200 Kelvin, that puts us about here on the graph, and 5.2 atmospheres, when we plot that point, we end up here in the solid region, so the phase at that temperature and pressure will be solid. Now, line C is right here, and line C is the border between liquid and gas. So the phase change or changes that are occurring along that line are either going to be evaporating or condensing, evaporation or condensation. All right, so now let's talk about classifying matter. Matter is defined as anything that has mass and takes up space. That means everything we see in the universe with our five senses is matter. We tend to think of things like air as not being matter because we can't feel them on a daily basis, but if you're driving in a car and stick your hand out the window, you're going to feel that air. So matter is basically everything in the universe that we can see. And matter can be broken down into two categories: pure substances and mixtures. So pure substances consist of elements and compounds, and mixtures can either be heterogeneous mixtures or homogeneous mixtures. Now we'll zoom in on each of these and define what they are for you. All right, so let's first talk about pure substances. A pure substance is defined as a substance made of only one type of particle. All right, and pure substances, again, can be either elements or compounds. So let's go ahead and talk about elements. Elements are made up of atoms. They're the simplest form of matter. Let's go back to that chunk of copper. If you have a chunk of copper and split it in two pieces, you're going to have two chunks of copper. If you keep splitting that copper over and over and over and over and over again, once you get to the smallest possible unit of copper that you can have, that is called an atom. Right, now, atoms cannot be broken down into simpler substances. They are the simplest form of matter. We can find elements and their atoms on the periodic table. Now, the symbols you're going to see on the periodic table will all be made up of at least one capital letter and maybe a lowercase letter following that capital letter. So if you're asked to identify an element, or if you're given a symbol and asked whether it's an element or a compound, you'll recognize the element because it'll only have one capital letter in the symbol. Here are some examples. O2 is oxygen, Na is sodium, S is sulfur, and H2 is hydrogen. Now we can see that each of these contains one capital letter. Now, when you see this little subscript of 2 after oxygen, that just means that there's two oxygen atoms bonded together, kind of like in this picture here. We have two of these pink circles. These would represent our oxygen atoms chemically bonded together. But since it's all oxygen, it's still considered an element. Now let's look at compounds. Compounds are made up of molecules. If you have a glass of water and you keep dividing that glass of water until you have the smallest unit of that water, it will be called a molecule. Now, molecules are atoms of different elements that are chemically bonded. Remember, if the two atoms that are chemically bonded are the same element, we consider it an element. But if the atoms bonded together are of two different elements, we consider it a molecule. Now, molecules can be broken down into similar substance because we can take this yellow circle and this orange circle and split it apart to have an atom of orange and an atom of yellow. Now, when you're looking at the symbol of a compound, the symbols will be made up of more than one capital letter because they contain more than one atom. So examples are H2O, CO2, carbon dioxide, there's glucose, and this is a compound called sulfur dioxide. Now again, the subscripts tell us the number of each atom that we have in those compounds. So H2O means 2 atoms of hydrogen and 1 atom of oxygen. CO2 is 1 atom of carbon and 2 atoms of oxygen. Take a moment and pause the video, see if you can work out how many atoms of each element are in these two compounds. Alright, so glucose will be made up of 6 carbon atoms. Each molecule, will be made up of 6 carbon atoms, 12 hydrogen atoms, and 6 oxygen atoms. And sulfur dioxide will be 1 sulfur atom and 2 oxygen atoms. Now let's look at mixtures. A mixture is a substance that's made up of more than one type of particle physically mixed together, not chemically, and that becomes very important later. So let's first talk about a heterogeneous mixture. The prefix hetero means different. So heterogeneous mixtures will have a non-uniform particle distribution. In other words, the particles will be distributed in the mixture randomly. So when we look at this picture here, I have a compound and a couple different elements. Now, there's no pattern or organization to the way these particles are arranged, so we would say that that mixture is heterogeneous. The particles in a heterogeneous mixture are relatively large, and that means they can be that a heterogeneous mixture can be separated with a filter. Right? Now, the particles in the heterogeneous mixture are so large that when you try to pass them through a piece of filter paper, they're too big to fit through the little pores in the filter paper. Now, because of this, a heterogeneous mixture will also settle out over time. If you have put a solid like sand in water and shake it up, the sand will be all floating around in that mixture, but eventually over time it will settle out. Examples of heterogeneous mixtures would be raisin bran, human beings, or any other animal. We're all mixtures of different things and all randomly mixed together. Or dirt, soil that we see. There's little rocks scattered through it, little bits of quartz, red sand, black sand, topsoil, etc., etc. So homogeneous mixtures are the exact opposite, basically, of heterogeneous mixtures. Homo means the same, and so we'll have a uniform or patterned particle distribution. And if we look at this diagram, you can see that each white circle is surrounded by 4 blue circles. It doesn't matter which white circle you look at, each one is going to be surrounded by 4 blue circles. And if you were actually able to zoom in on a homogeneous mixture so that you could see the particles, you would see this patterned arrangement of the particles. So in a homogeneous mixture, the particles are very small. That means you cannot separate a homogeneous mixture with a filter because the particles are small enough to pass through the pores in the filter. That also means that they will not settle out over time. Now, a homogeneous mixture also has a special name called a solution. We're going to look at solutions a lot in Unit 9 at the very end of the school year. Now, the examples of homogeneous mixtures are salty water, air, or steel. Steel is kind of an interesting one. It's actually a mixture of iron and carbon. And when you change the proportions of iron and carbon, you change the properties of the steel. If you want your steel to be more flexible, you put less carbon in. If you want it to be more less flexible, more brittle, you put in more carbon. Now, these characteristics of these two mixtures can be used to identify them. Right? Just ask yourself, can I separate this mixture with a filter? Are the particles distributed randomly, or is there a pattern that we can see? Will the mixture settle out over time? So here are some mixtures. Take a moment, pause the video, and ask yourself that question for each of these mixtures. Can you filter it? Will it settle out over time? And are the particles arranged randomly or in a patterned way? Okay, so vegetable soup. I don't see any patterned arrangement of those particles. It's a mixture of the liquid broth and the solid vegetables, so we could easily filter out the solid vegetables, leaving the soup behind, so that is a heterogeneous mixture. Coca-Cola, it's not really easy for us to tell if there's a uniform particle distribution, but when you drink a glass of Coca-Cola, it tastes the same all the way down. So you could assume that the particles are arranged in a uniform way, but think about the other two questions. If you run Coca-Cola through a filter, are you going to get all the caramel color and sugar stuck in the filter and just pure water down below? No, the Coca-Cola will pass right through the filter and it won't settle out over time if you leave it in your refrigerator, so that's a homogeneous mixture. Now here's an example, muddy water. I kind of talked about that in the last slide. If you put sand in water or dirt in water, eventually it will settle out over time, and you can separate muddy water by filtering out the sand, so we call that a heterogeneous mixture. Kool-Aid is a homogeneous mixture for the same reasons that Coca-Cola is a homogeneous mixture. And fog is a heterogeneous mixture because if you look at a region, maybe the first 100 feet of altitude, from where you're standing on the ground to 100 feet up, the fog is going to be all concentrated toward the bottom. It kind of settles out on the surface of the earth, so we consider fog a heterogeneous mixture. All right, and that's it for discussion 1-1. If you have any questions about this, please bring them to class, and thank you for watching. Please like and subscribe.